Hi, welcome back to our lecture, our practical guide to quantitative finance interviews. Today, it's a quite important lecture. We are going to talk about the option pricing, which means we are going to introduce both the Black-Scholes-Moulton model and also the Black-Scholes differential equations. Okay, so before we start to talk about all these things, I want to brief you through all the foundation materials or formulas that we are going to use during this lecture. So the first one, please recall the Ito's lemma, where if we have a function of time t and some function xt, okay? And we are going to have Ito's lemma as dft(xt) should be equal to what? The function according to t dt plus the first derivative according to x txt dxt plus 1/2 the second derivative, where we take derivative according to x for 2 times of txt multiplied by the derivative of xt for its square. Okay, so if you don't know how can we derive that, please come back to the last lecture in the previous chapter. That is talking about Ito's lemma. Okay, and now let's start. Let's think of a general process. Okay, we define a WT, which is a Brownian motion. Okay. Where t should be larger than or equal to 0. And now we are going to introduce the generalized geometric Brownian motion. So why do we need that? Because we are want to pricing some kind of asset, and a value of an asset usually in most cases in reality should be a positive number, right? It's almost impossible for a value of the asset to be negative. So if we are using the original Brownian motion, it can either be positive or negative. Then that's not what we want. But how can we convert both positive or negative thing to non-negative? Taking exponential, right? So it's related with the log normal distribution. We can define it in this way. So if we define our new xt as some kind of function sigma s multiplied by dws, which is a Brownian motion, and take the integral from 0 to t plus the integral from 0 to t of some function alpha s minus 1/2 sigma s squared ds. So these two are just the two random functions that we can choose from, okay? And this is just the square of the first function. And if we define such a process, then what can we find? We can find the dxt, which is just removing those two integrals, should be sigma t dwt, right? Plus alpha t minus 1/2 sigma square t dt. Okay. And if we take the square of this dxt, what is going to happen? Well, basically, we do not have these items because now we are only considering the dxt part, okay? So this becomes square t dwt dwt. And now, if we consider an asset pricing process, which is ST, which is the stock price, okay? stock price, which is equal to some kind of S0, the price at initial point, multiplied by the exponential of this xt. Then this could be non-negative, okay? And if we take the derivative of this st, it is gonna to be just the same as take derivative of a function xt, right? If we define this function as this xt, and by applying the Ito's lemma introduced here, what can we get is that this should be equal to the f prime xt multiplied by dxt plus 1 over 2 f double prime xt dxt dxt, right? And we know this part is just this, and this part should just be 1 over 2 ext as 0. Because we are taking derivative according to t, then nothing is going to change here. We are taking derivative according to xt. So if we denote this as something else, let's say delta, then basically nothing changes here, right? And this is also the same, which is just S0 ext. And we know this part is just st, and this is also st, right? So it just becomes what? It is gonna to be equal to st dxt plus 1 over 2 st dxt dxt, right? And now we can take one dxt out. We can take one dxt out, such that it is going to become alpha t, which is defined here, st dt plus sigma t st dwt. Okay, so basically we are just trying to taking one thing out, and this is, well, this is going to be the result of dst. Okay, so let me explain this in detail. So we already have dxt, which is gonna to be sigma t dwt plus alpha t minus 1 over 2 sigma t squared, right? dt. And let's first take one dxt out. So we have this sigma t dwt plus, let's denote as something bt. Okay, let's denote this as, oh, not bt. bt is overlap with Brownian motion. So let's denote it with some kind of ct for convenience, okay? And this is going to be ct dt, right? When we take this one out, and another bracket within it, it is going to be st plus 1 over 2. We can also take one st out. So this is going to be 1, and we have a st in front of it, okay? 1 plus 1 over 2 dxt. And for this part, we can separate it out so that it is going to be just 1 over 2 sigma t dwt plus 1 over 2 ct dt, right? And we need to know one important thing, that for Brownian motion, dwt square is going to be the same with dt. And dt dwt is going to be 0, and dt dt is also 0. And by combining these three back to this part and this part, when we take the multiple, we can find what is going to be left. We are going to have first item, we are going to have 1 sigma t dwt because it is multiplied by 1, right? And it is also going to be kept for the second part, which is ct dt, right? But for this part, we have dwt and also the dwt here. So we are going to have plus 1 over 2 sigma square t dt, because we have 2 dwt here. So combining together, it is going to be reduced to dt. And if we multiply this one with this one, then we have 1 dt and 1 dwt, so they are going to be canceled out. And now let's come to the third item. When we have dt with dwt, it's canceled out. If we have double dt, then it also becomes 0. So eventually, we only have these 3 items left. And we already know that ct is going to be what? Ct is just alpha t minus 1 over 2 sigma t, right? And so this part and this part canceled out. Eventually, we have the original statement where dst equal to st multiplied by sigma t dwt plus st alpha t dt. Okay, so this is the general case. Basically, all the things that all the non-negative and basically all the non-negative and time risk neutral things can be deducted by this general formula. Okay? But the interesting thing is that when we replace this sigma t, if we consider it as some kind of constant, sigma and alpha t as equal to mu minus 1 over 2 sigma square. Okay? And then what is going to happen? Then it is easily see that this one is our risk neutral definition. Okay, why is that? Because let's think in a more simple way, okay? Let's introduce one more new page. If we have st equal to s0 multiplied by e xt, where xt is going to be a constant sigma multiplied by wt plus a constant mu with t, right? So we know that x is going to follow xt. It is going to follow a normal distribution of mu t sigma square t, right? So what's the moment generation function? The moment generation function of xt according to S, it is going to be e mu t s plus sigma square Ts square over 2. And where we can easily find that the first order, which is the expectation of this St, is simply S0 multiplied by E when we take this as 1, which is mu plus sigma square over 2 multiplied by T, right? And what is risk neutral? What is risk neutral? Risk neutral means we cannot earn extra profit or premium but without taking more risk, which is if we have the risk-free rate, which is the risk-free rate, then ST should just be S0 multiplied by ERT. Okay, then we just make these two equations to be the same. We can have mu star. The risk neutral mu is just going to be what? It is just R minus sigma square over 2. And basically, this mu is just the R here, okay? We just eventually want to define our alpha t as something as R minus 1 over 2 sigma square. So I think these are all the pre-things that we need to know before we come to the real Black-Scholes-Moulton model. So now we can talk about the Black-Scholes-Moulton differential equation. The equation is written like this. So if there is a V, where V is actually a function of the stock price S and T. So basically any option is basically a function of S and T, right? And now this equation should always be satisfied under the risk neutral situation. So how can we get that? We can see the distribution here where you can see just what we did. We define X as the Ito process by a certain equation where we have a function before dt and another function before the dwt. Basically, that is what we are doing just now, right? We have a function before dt and another function before dwt. And by doing that, if the function is related with the discounted rate at some terminal time larger t minus than the current time smaller t, then it is going to be a martingale process which satisfies this equation, okay? And on the risk neutral measure, as we just know written here, is R here, which is just the risk-free rate. And then we are going to have the classic Black-Scholes-Moulton equation, okay? Which is just the first derivative according to t, and the first derivative according to s multiplied by r, and plus this 1 over 2 sigma square item, and it is going to be equal to r multiplied by v. And now let's introduce the Black-Scholes formula assumptions. There are in total 6 of them, and I hope you can remember all of them. The first one is that the stock pays no dividend. Okay, you can see we only consider the risk-free rate, but not the dividend ratio. And the second, the risk-free rate is constant and known. And this is a quite important assumption, which is led to the real part when we talk about the Greeks, because in reality, actually the risk-free rate is going to change. And third, the stock price follows the geometric Brownian motion with constant drift mu and volatility sigma. Okay, so you can see it does not require it to have R. It can be something like R plus something. Okay, and there are no transaction costs or taxes. The proceeds of short selling can be fully invested. This is also a quite strong assumption because in reality, it's actually more difficult for you to short selling something than just buy it. Okay, especially for individual investors. And all securities are perfectly divisible. It's also not true in reality because you can only buy 1 hand, 2 hand, right? But you cannot buy like 0.01 hand of something. And last but not least, there are no risk-free arbitrage opportunities. That's basically the risk neutral thing. It means that you cannot get extra premium or profit without bearing more volatility. And you can see from our derivation here, you can see if we want something more, okay? If this becomes R, the risk-free ratio, then if we want something more, the only thing we can get is to increase this delta part, right? If mu is already fixed as R, this is R minus sigma squared over 2, right? If it is written like that, then the only way we can increase the total value of X is to increase this part, the sigma related part. Okay? Then sigma is related with volatility. Basically, we are bearing more risks. And now let's come to the Black-Scholes formula. The formula is just easily derived by the option, by a European call option. You know, the European call option gets profit by ST minus K with only positive value. And if we plug that into our original equation and take all the integrals, you can get this one, which is this call is just the stock price S multiplied by the discounted part, which is E negative Y tau. Tau is just the T minus T. And this is going to be NDE, which is just the distribution, the normal distribution value of D1, and minus the K part, and E negative R tau, and D2. And there is also an important relation between D1 and D2, where D2 is just D1 minus dot sigma multiplied by square root tau. Okay? So if the underlying asset is a future contract, then the yield R is going to be, yield Y is just R, the risk-free rate. But if it is a foreign currency, then it should be the foreign risk-free interest rate. Because, you know, for USD or CNY, the Chinese yuan, their risk-free rate is different. Currently at China, it's around 2%, I think. But US, if you are following the market, you know it's already super high, right? It got a lot of hikes this year. And how can we derive this one? The derivation is actually quite simple. So as I just told you, we just need to put in the call. So the call's value at initial stage should be what? Should be E negative RT on the risk neutral setting. If we just derive tau equal to T minus 0, which is just T, okay? For simplification. And this is going to be the expected value of ST minus K plus, right? It should be non-negative. And we already know that our XT on the risk neutral should be equal to sigma Brownian motion WT plus R minus sigma square over 2 T, right? And then it follows the C0 is just going to be E negative RT expectation of S0 E sigma WT plus R minus sigma square over 2T minus K, right? And this should be non-negative. And now we can see the only part we need to derive is this part. Okay? And this part, we can separate them out, which is just E ST minus K plus. It should be equal to the first part, which is from negative infinity to positive infinity, S0 EX minus K plus, right? And what's the density function? This is basically the value of itself. And what is the density function of the x? We recall that xt actually follows what? Follows normal mu t and sigma square t, right? So we can have the density function, which is just the normal distribution function, 2 pi multiplied by t, right? The t should be within the square root, okay? And exponential function of 2 sigma square t and negative x minus mu t square dx, okay? And we know this can only be positive, so we can only consider the place where S0 EX equal to K. And this, we can have X is going to be equal to K divided by S0 log, right? So now the new equation just becomes log K over S0 to positive infinity. And then we can remove this positive sign, right? And it will become S0 Tx. And we can separate these two parts out. Basically, let's call this total part as A, okay? Let's call it as A. So this is just multiplied by A minus K, because K is just a constant, over log K divided by S0, positive, infinity, and A. And this is dx, this is dx. And can we further reduce that? It is possible, because for the second part, this A here, 1 over sigma 2 pi t e 2 pi t square negative x minus mu t square, right? So if we denote y equal to x minus mu t over sigma square root t, and then we can have dy is going to be what? Dy is going to be dx over 1 over square root t, right? And then when we plug it back, this part, it is going to become k over 2 pi and from square root t log k as 0 minus mu t, and this suddenly becomes e y square over 2 dy. And if we consider this part, this is just n of the sigma square root t log k as 0 minus mu t, right? So it is only this value. And we can do the similar thing to the first part, and then we can become, it is going to be n c plus square root t tau multiplied by S0 minus the k and c, where this c is just d2, which we rewrite it here, right? And this d1 is just our c plus sigma square root tau. Okay, so you get that? We are basically just trying to plug in and do integration and then change the variables to solve out all the equations. And now let's come to the questions. So the first question is that assume 0 interest rate and a stock with each current price at 1 that pays no dividend, good, which fits the Black-Scholes model assumption. Okay. And when the price hits level H, where H larger than 1 for the first time, I can exercise the option and receive $1. And what is the option worth to you today? And please remember there is 0 interest rate. First, let's use a brute force approach to solve the problem by assuming that the stock price follows the geometric Brownian motion on the risk neutral measure, okay? And then we have what? We have ds equal to rs dt plus sigma s dwt. And we know that r is 0, so this part is canceled out. We only have sigma s dt, and then we are going to have d log in s is going to be -1/2 sigma square dt plus sigma dwt. Okay, because the mu part is gone. Okay, because the mu part is gone. This is just our original speaking one dxt, and we know that in the risk neutral place originally it is mu -1/2 sigma square, and mu is just equal to r, right? And now we have r0, so that's why this part is gone. So we only have -1/2 sigma square here, but the second part is just the same. And we have S0 is going to be 1, right? At 1 today. So we also have log in S0 should be 0. And we also have log in S. And so since the initial stage it is 0, you can say log in S can also be reduced to a Brownian motion, where we can define a WT is just what? It's just a log in S plus 1/2 sigma square divided by sigma. And the interesting thing is, what can we do next? Okay, we are going to replace because it is already proved to be Brownian motion, then it is a martingale. And then for martingale, remember the exponential one, where we have zt equal to exponential lambda wt minus 1/2 lambda square t. And we can do the same thing where we take the expectation of zt. It is going to be the expectation of exponential, where we put our equation into that. Lambda multiplied by sigma, and on the numerator, it is log in s plus 1/2 sigma square t. Oh, there is a t, sorry. And minus 1/2 lambda square t, right? And it should be equal to 0 because the initial stage should be 1. And so e to the power 0 equal to 1, okay? And then we can choose any delta so that we set delta equal to sigma. And so these two cancels out, and this part cancels out, and we get what? We get expected value of exponential log in s should be equal to 1, right? And now we can using the martingale setting, where let's say the probability that log in s even reaches log in h, it is going to be probability. Let's write it down, okay? Probability that log in s reaches log in h. And then we have probability multiplied by the expected return, which is log in h plus 1 minus p exponential of negative sigma And we know this part is just 0, so we cancel it out. So this is equal to 1. So we have pH equal to 1, and price should be 1 over h. Okay, so this is the price. So this should be received h, okay? Because if you receive 1, then according to the time value seen, it's not so valuable, okay? And now let's continue the second question, which is also the last question today. I know it's a long lecture, so keep going, okay? Assume a non-dividend paying stock follows a geometric Brownian motion. What is the value of a contract that at maturity t pays the inverse of the stock price observed at maturity? So again, this time we can use the Black-Schoen differential equation. We first define V equal to 1 over S, and on the risk neutral again, ds is going to be Rs dt plus sigma S dWt, right? And applying Ito's lemma, well, we have the Bronchial. We can have dV is just equal to what? dV ds Rs plus the derivative dV dt plus 1 over 2 d square v delta s square, right? And sigma square s square. And it's all multiplied by dt. And also we also have a second part, which is v s sigma s dWt, right? This is the Rs here. And we know the V2S is just negative 1s squared, right? And the second derivative is 2 over s3. And when we plug in that, we can have actually dV is going to be negative r plus sigma square multiplied by 1 over s dt. And we can replace this as v, okay? And minus sigma v dWt. Okay, so we can find what? V also follows a Brownian distribution, geometric Brownian distribution, with negative r plus sigma square. And then we can apply the Ito's lemma again. We can have the d log in v, which is just our original x. And this should be equal to negative r plus 1 over 2 sigma square dt minus sigma dWt. Have you found the trick? If we take the longing of some geometric Brownian motion, we simply, what we need to do is to negative 1 over 2 sigma square here, and remove the v here, and remove the v here, and keep the original part for the second component. Okay, so we can easily reduce to this equation, and we can have what? We can have log in v actually is going to follow a normal distribution. Right? And what is distribution? It is going to be negative r plus 1 over 2 sigma squared t. And this is just sigma squared tau. Okay, let's write it as tau, which is just t minus t. And we can have E expectation of V at eventual time is going to be exponent E expectation of E log in VT, which is just ST 1 over ST, which is the value, and multiplied by the probability function, which is just the mean of expectation of this law in V, which is just negative R plus 1 over 2 sigma tau, right? And then we can have the expected value of Vt at current stage. It's just we multiply this with negative R tau with expected value of V at the eventual time, which is just 1 over St multiplied by E to negative 2R plus 1 over 2 sigma square tau. Okay, and actually, if you can find this answer is different from the answer from Green Book. The Green Book one is wrong. Okay, it has a typo there, so please use this one. And we can see if we combine these two questions together, you can see the step is quite similar. We first define the risk neutral setting, and then we take the law-in of something that we already know it follows a geometric nonlinear distribution, and then try to combine them together to find the pattern. For example, to find it becomes a martingale, or to find it to follow certain kind of distribution, and then we take the expectation of that to solve out the final answer. Okay, so I guess that's all for today. And again, you can also apply the first question solution to the second question. You can also get the correct answer. So that's all for today. Next time, we're going to be talking about the Greeks of options. Thank you for watching.